All right, let's do a kinetic analysis of cycling. All right, to do a kinetic analysis of cycling, we identify all the forces acting on the object, and then we understand that object's acceleration. So here's a terrible stick figure of a bike, but two wheels, the frame, and a person pedaling. And our job is to add up all the forces acting on the object, and we'll understand the product of mass of the bike rider system together and the acceleration of the center mass. And that center of mass would be the center mass of the bike rider system together. So let me put that here. M, mass of bike plus rider. Okay, so it's combined. This is our system that we're going to analyze for a kinetic analysis. All right, so let's identify forces acting on the bike rider. So we're not going to be identifying forces created by the cyclist. We're not going to be identifying the force of the foot pushing on the pedal, not for this part of a kinetic analysis. We're going to do the bike rider system together, so we can sort of forget about the biker here, the cyclist, and just think about this whole thing together. So what forces are acting on this bike rider system? Well, the ground is pushing up on the wheels, and I'm going to do F, ground reaction force, and this can be rear wheel. And I'm just going to put the vertical listed there. And this would be F, GRF, front wheel. And again, just the vertical in terms of the way I'm going to set this up right now. What other forces? What are the pushing or pulling on the bike rider? We have gravity. So I'm going to draw the center of mass of the bike rider system there. And I'm going to put an arrow right here. And I'll put a label, I'll put the label ref G, F of gravity, okay? And let's see, I better keep a list of all these. So I'm gonna put a list over here. I'm gonna put FG, gravity. Gravity is the force acting on the bike rider system. F, GRF, and now I'll abbreviate front, vertical, F, GRF, rear, vertical. Okay, so we're keeping a list. So these are ground reaction forces, vertical direction. All right, what other pushing or pulling happening on the bike rider? Well, I'm going to put drag force due to air. All right, F, drag. I'm going to add that to my list. Air resistance. Okay. And I've drawn this as an opposing force. This direction of this force vector does depend on which way the air is moving over the cyclist. So it's nice to start with the idea that the air is moving over the cyclist and the sagittal plane as we're looking, but it may be a tailwind, or maybe the wind is coming at the rider from the side. But for now, we're just going to start with the drag force opposing the direction of this cyclist right now. Okay, those are some of the obvious ones. There's a couple that are not so obvious. One is I'm going to draw a force vector right here. I'm going to try to make it big so we can see it. And I'm going to do the same thing right here. And what these two are called rolling resistance. This is the resistance to the wheel rolling over the surface. Think about rolling or riding a bike on a mountain bike with really, really soft tires. as you try to pedal, the mountain bike is a little hard to get moving. But if you think about a road bike that has a narrower tire, a little bit more air pressure, it's a little stiffer, it's a little easier to roll over the ground. That sense of how hard or easy it is to roll an object over a surface is rolling resistance. Now, sometimes I'll actually talk specifically about bearing resistance, and the wheels have some resistance to rotating around the hubs. That is, if I just pick the bike up and I spin the wheel, it will spin, 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 and eventually come to a stop. That force causing that wheel from stop rotating, it would be related to bearing resistance. Right now, I'm actually going to enfold that resistance, any resistance to rolling, into rolling resistance forces. Now, I have a rolling resistance at the rear wheel and a rolling resistance at the front wheel. So I'm going to put FRR rear and FRR, that's NAR, 2 R's, front. Okay, and then I'm going to list them over here. FRR rear, FRR front. And these are rolling resistance. The resistance to a wheel rolling forward. We've done some neat work on trying to figure out factors that influence that resisting force. Okay, so let's see, what else do we have? Well, another one that's not so obvious is the propulsion force for the bike rider system. Now, we would like to think that it's right here where the pedals are, but that's not actually the force that's causing this whole thing to move forward. What's happening is I push on the pedals turn the crank pulls on the chain pulls on the rear wheel. The rear wheel tries to rotate like this and then comes up against the surface of the ground, pushing on the ground, and then the reaction to that pushing is the propulsion force. So I'm actually going to put a force right here, and I'm going to do F propulsion. This is what makes the bike go forward. This force right here. I'm going to list that here, F propulsion. All right, that makes the whole bike rider go forward. Same thing like in your car, you push on the gas pedal. The gas pedal is not making you go forward. What's making you go forward is the engine that drives the rear wheels, and the rear wheels try to push against the surface. There's the inability of the wheel to spin on the surface, and then there's a propulsion force. Okay, so that's what's moving our bike forward. And there's one more force that we're going to deal with. And I'm going to add it over here on my list. It's a little hard to draw it on here when I've drawn the bike on a level surface. And that's the force of biking uphill. Or if you're biking downhill, how you may actually get an additional force helping you move forward. So I'm going to write that right here, and it's going to be F slope. This is the force of going uphill or that opposes the direction of movement or going downhill. All right, so now let me explain that one in using a different picture. So here is, think of this as the bike rider going uphill, and I'm going to draw an arrow like this, indicating that the box is trying to go uphill. Where's the slope force? Well, I'm going to draw out the force of gravity, and this is obviously a hill going uphill. And I'm going to draw a force of gravity as a vertical force, vertical relative to the flat surface of the earth. If we can extend that out, we can see that. That's FG. Well, now, if we take that force vector, the box is going up this hill. That force is not acting in the direction of movement, nor is it acting perpendicular to the direction of movement. So I need to decompose this force vector into two components. One that's parallel to the surface of the going uphill, and one that's perpendicular to the surface. The way I do that is graphically, I draw out a box so that the force arrow vector head is at one corner of the box, the tail is at the other end of the box, and this box is parallel, this edge is parallel to the surface, and this edge is perpendicular to the surface. Once I do that, I actually identify my force vectors, this one right here, and this one right here, the sides of those boxes. This one is F parallel, so I'm going to do two parallel lines, and this one is F perpendicular. That's perpendicular to the surface. Let me write this out down here. F with two lines, that's not the number 11, that's parallel. Parallel component of FG. F perpendicular is perpendicular component of FG. We're going to need to know these, because if I'm looking at the movement of the cyclist going uphill, this force vector, this component, opposes the direction of movement uphill. Now, if I'm going downhill, this force vector will aid in going downhill. This force vector is only going to come into play if we're interested in the vertical movement of this box on this surface. And we're not, if I look at it this way, I'm not interested in whether or not this box goes up and down relative to this surface. I'm only interested in whether this box is going uphill or downhill. Sorry, a little breeze in here. Okay, so this is the slope, and we'll call this slope force. If you look at this angle of the hill, as this angle goes up, this force component gets bigger. As this angle goes down, that force component goes to zero, that parallel component. I'll do a separate video on that part. Okay, but for now, we have this parallel component, which is the slope force. Let me go back over to my bike, and that's this force right here, F parallel. And you can see now why I can't draw it when I'm on a level, because I can't draw a parallel component, because there is no parallel component when we're biking on the level. All right, so now I want to ultimately put these forces into this equation, F equals ma, and now I need to identify which direction I'm interested in. Well, if I'm interested in vertical forces, I would look at gravity, ground reaction force, and that's it. But I'm really not interested truly in whether the biker is going up and down, at least not now. Maybe later on we may find some interest in that. I'm really interested in the horizontal movement. So these are all vertical forces here. Vertical. I'm interested in these horizontal ones. Now I need to assign a direction with each of these force vectors. And I'm going to use forward as positive. Therefore, drag force, I'm going to treat right now as a negative force, because it's resisting movement. At least right now, that's how we're going to deal with it. Rolling resistance is pushing against the cyclist, trying to slow it down. So that's a negative one. That's a negative force, front and rear wheels. Propulsion is obviously moving or trying to move the biker forward. So that's a positive force. And then slope, if I go back to my other picture, if I start going uphill, that will be a negative force. Now I'm going to put a little side arrow here. This is going uphill. If I'm going downhill, that could be a positive force, because it's going to aid moving downhill. All right, good. So now let's take all those forces and put those forces into our equation, F equals ma. And that mass is the bike rider system, and that acceleration is the center of mass of the bike rider system. Now I'm just going to start listing the forces, and I'm going to do the horizontal direction. I have F propulsion, I'm going to abbreviate, as a positive force, plus rolling resistance, and I'm going to combine those two rolling resistance into one rolling resistance force, plus slope, I'm going to consider only going uphill right now, plus drag. And I'm only going to consider that as a negative force. We add up all those and we get MACOM. Sorry, I went over too long on the line here. This is all the same equation. Now, what I'm going to do is, let me write it again, and I'm going to just draw these out as all negative signs here. So I'm going to have F propulsion minus F rolling resistance, that's the two wheels combined, minus F slope minus F drag equals MACOM. I'm going to simplify this even more, and I'm going to look at all these, and they're all negative, and these are all resistance forces. So I'm going to write this out one more time, just so it's easier to talk about this in general. Propulsion minus resistance equals MACOM. This is our general equation for biking. If we know the propulsion force, and if we know all the resistance forces, we can understand the kinematics. The resistance forces come from rolling resistance, slope resistance, and drag resistance. Okay, so that's our general equation for our kinetic analysis, and we're going to need to use this as we start talking about why cyclists buy light gear, why they want their bike to be as light as possible. We'll talk about cycling power. Power is not in here yet, but we need this equation in order to do that. Okay, so that's our kinetic analysis leading to F equals MA. Okay, thank you.